Hi everyone, welcome to Deep Learning Talks. In today's video, we're going to talk about the GPT family. The early GPT family, let's say the GPT-2 and the early GPT models. So these models were decoder-only transformers. So today also they are decoder-only transformers. But let us try to understand what were or what are decoder-only transformers. So let's try to go through each block by block or each stage by stage. In the early part of our Deep Learning Talks playlist, we have seen that every token is converted into token embeddings. Then, along with token embeddings, we have something known as positional embeddings. Token embeddings and positional embeddings get added together and they become input to the transformer. Now, what is a transformer? Transformer is nothing but a neural network, right? We have known the significance of token embeddings. We have known the significance of positional embeddings. Why positional embeddings? Because we are not here dealing with recurrent neural networks. We don't understand where each token is located. We want a way, a mechanism to be able to store its location, to be able to store its position in the whole vocabulary. Along with that, why token embeddings? We want to model each token as a vector. We want to represent each token as a vector. And the vector is going to have a dense representation. It's going to be a dense vector. What I mean by dense vector is maybe it's a 512 dimension vector if a smaller model is considered. But largely, we will have huge vectors, right? We can have 1024 dimensional vectors also. What that means is if I have one token, then I have 1024 dimensions for that particular token. If I have a million tokens, then I have 1024 cross 1 million or multiplied by 1 million such elements that are representing all of my 1 million tokens, right? So we know the relevance of token embeddings, we know the relevance of positional embeddings. Together they are added, and let us assume that the dimension of both of them is dk, right, or simply d, right? Together they are added. It's a simple element wise operation. People who have understood or learned linear algebra, it would be very trivial for them to imagine one matrix being added with another matrix. That's it, right? So let's say we have 1 million tokens, or let's say let's imagine a realistic sequence length or a context length. Let's imagine 1024 sized context length. 1024 size is the context length. That means I have 1024 tokens, and each token is represented as 512 or d dimension vector, right? So 1024 cross d is my positional embeddings, 1024 cross d is my token embeddings. I just add them. I add this information. It's a simple linear operation, element wise. That's it. Now this matrix together acts as the input to the transformer. Now what is going to happen in the transformer? We're going to have an attention block, right? Now what will the attention block do? Each attention block, or let's talk about attention block. Let's not say each attention block. So the attention block is going to compute an attention matrix. So attention matrix is nothing but the contextual representation of the whole vocabulary of all 1024 tokens. What do I mean by contextual representation? How each token is contextually related to other token for every two pairs of token, right? So we're going to have an n square matrix, right? So all 1024 tokens on the horizontal axis, all 1024 tokens on the vertical axis, and the score between them. The score between every two tokens is going to be stored in the attention matrix. Now this is one head of attention. We can have multiple such heads. Let's say we have four such heads of attention, right? And what is the objective of attention? So the objective of attention is to compute contextual representation, the relationship between two tokens, the similarity, the context, right? So one head might capture one set of relationship, other head might capture another deeper hierarchical relationship, and we can have multiple such heads so that we understand the language better. So that we understand the whole vocabulary better. Now, before we move forward, let's first also talk about the objective. What is the objective of everything that we're doing? What is the objective of GPT? What exactly is GPT if you were to summarize? So, we are trying to build a next token predictor. A next token predictor is being built on the whole internet data. The whole internet data is compressed into the text file, right? Now, this text file is going to be fed as a training data. Now we are going to train a transformer or a neural network to predict the next token in the sequence, to let it behave as the next token simulator, right? We want to enforce the behavior in GPT such that it behaves as if it is auto-regressively in a loop predicting the next token after the next token. This is the objective function of a transformer that is acting as the architecture behind GPT. Right now, the first thing is input that we've already talked about. Then the second thing is attention that we've already talked about. After attention, we do one more operation, which is residual, adding residual and normalizing. Right, so we call it residual plus add norm. Right, so what do I mean by this operation? What does this sublayer do after attention? What we are doing is, when we say residual, we simply mean that, let's say you have your input x. Now f of x is the function that is acting on this input. When you do a transformation that gives you f of x, so what happens in residual and add norm or layer normalization? What really happens? So imagine that your input is noted as x. The output of any sublayer is noted as f of x. Let's generalize it. Any sublayer that it produces, it takes in an input x and it produces an output f of x. When you add in input to f of x, which is you do x plus f of x, right? You're adding input to the output of the sublayer. This is known as adding the residual. Then you apply a transformation or normalization that is known as layer normalization. Now that layer normalization is going to help you stabilize the training. It's going to have some scaling and shifting operations, and it's going to help you stabilize your training. That's it. And it's going to improve your gradient flow. Now attention sublayer is sorted, residual and add norm is sorted. Now what is going to happen? Now we are going to feed it to the feed forward neural network. The feed forward neural network is going to help us, you know add in fusion more and more nonlinearity and help us simulate the next token prediction flow. So feed forward neural network is largely the same. It's pretty simple. There is no complexity. We might have, or we will have, a softmax at the end that is going to produce probabilities as acting as our output head. Those probabilities will help us, sample the next token in the sequence, right? But the main thing that we have to talk about is not attention, not residual add norm, not feed forward neural network. But there's one important concept. Why do we call this as a decoder only transformer? So one simple reason is we don't have an encoder in this. In the original paper, attention is all you need, the original transformer that was introduced for machine translation, the encoder used to read the entire input sequence, and the decoder generates the output sequence token by token. This is what used to happen in the paper attention is all you need. There we had described an encoder decoder transformer. So we have three types of transformer that we are going to discuss in the future: encoder decoder, decoder only, encoder only. Right, so we have removed or gotten rid of encoder stack from the encoder decoder transformer. We only have the decoder stack here. That's why we call it the decoder only transformer. Now there's one more portion that I would like to talk about, which is a little different in case of GPT, which is the idea of masking. So what basically masking suggests? So we also call it causal masking. We want to enforce the behavior in GPT to predict the next token. We are going to, this is the main objective function. We're going to use a cross entropy loss function to complete our objective, and we're going to use the idea of maximum likelihood estimation for the next token. And that's it. So what is masking and where does it come into picture? So since during the inference time, during the querying time, when the GPT model is ready, we want to inference, or we want to query by giving it a couple of sequences of tokens, and we want it to predict the next token. Without seeing the next token, we want it to predict the next token. So during the training time, what we do is we mask the future tokens. Now what do I mean by that? What do I mean by mask the future tokens? Masking means, let's say that we dead or we blur or we nullify the future tokens. How do we do it? We mark them as negative infinity. Now what counts as future tokens? So masking happens during the attention block when we are computing attention. So when we are computing that order of n square matrix, that we just saw on the screen, we saw that it has 1024 tokens on the vertical axis and 1024 tokens on the horizontal axis. Let's imagine a simple token sequence. Cat sat on the mat and ate the bat, right? So when I'm standing at cat, what do I mean by that? When I'm computing the attention for cat, I will not be able to see all the tokens that are on the right hand side of cat, which is sat on the mat and ate the bat. I will not be able to see anything that comes after cat. So for any token I, it can see all the tokens starting from 0 to I minus 1, right? Or let's say 0 to I. So all the tokens that are there in my scope for computing attention are less than me, right? Less than me, not in terms of any computing or quantifying power, but basically they lie on the left hand side of me, right? I cannot see what is about to come in the future tokens. So if I'm standing at sat, I will only be able to see cat and sat. If I'm standing at mat, I will be able to see cat sat on the mat, right? I will not be able to see what is there in the next tokens, which is the bat, and ate the bat. I will not be able to see that. So if we want to say it mathematically, or any token I can see all the tokens j where j is less than equal to I. That it cannot see I plus 1, it cannot see I plus 2, it cannot see I plus 3, where I is the relative position. That's it, right? So let's say I ranges from 0 to k, where k is the vocabulary size. So mathematically, when we say it cannot see, when we say we mask the token, what we really mean is we mark all of the future tokens, which is the upper triangular matrix. Mathematically, we'll see that we mark them as negative infinity. Why negative infinity? Because we eventually want to apply softmax on the attention scores to convert them into probability mass. So when softmax sees negative infinity, it will make it close to 0, or it will make it tend to 0. That means the model will that means the model will assign 0 attention to future tokens. So this helps us, this helps us enforce the consistent behavior. What is consistent behavior? That during training we can't see future tokens. During inference we anyways don't have future tokens. When the user is querying or inferencing, the user wants GPT to produce future tokens. It wants it to complete the sentence, it wants it to answer the question. So, and during training we are enforcing every particular sequence to act or to be able to behave in such a way that it does not see the next token and it has to predict the next token. We can also simplify it by saying that each token can attend to itself and all the previous tokens that it has seen. We can also say that since we are talking about token and the previous tokens, that we might have a natural left to right direction. We are not going bi-directional, we are going from left to right, and we are also trying to enforce the next token prediction, which is obviously the main objective of the GPT model. Okay, so we can also say that each position in the sequence is trained to predict the next token, right? So it's all about predicting the next token. Now there's one more architectural difference that I would like to highlight, that the positional embeddings that we talked about are also trainable, right? What do I mean by that? We don't use a static mechanism to generate positional embeddings. Instead, all of those positional embeddings are learnable. For example, if we have 1024 as the context length, as the fixed context length, and each position of a token is represented as a d-dimension vector. That means we have d cross 1024 learnable elements that simply represent position. Although there are a lot of disadvantages or trade-offs to it, because positional embeddings does not necessarily is helping us, in the next token prediction or is in the reasoning part, right? So there are a lot of trade-offs and the learnable parameters dramatically increase. Now that all the positional embeddings we have to memorize, we have to learn, and we have to update during training, the learnable parameters dramatically increase. So we obviously know that all the token embeddings are learnable. We also know that in attention, the key, query, and value matrices, which is WK, WQ, WV, are learnable. Multiple heads of attention gets computed. WO as a projection matrix is also learnable. And along with that, all the weights and biases in the feed-forward neural network are learnable. Along with that, we can also have scaling and shifting vectors in normalization part also as learnable. So positional embeddings here in this case dramatically increase the number of learnable parameters. If we have 1 million tokens and we are representing it each position as 512 dimensions, so we have 512 million parameters that we have to learn extra and that are not really helping us in reasoning, right? So there are some advantages and some disadvantages to it. So we're going to discuss in the future videos on what can we do to improve it and how the modern LLMs like the GPT-5 have resolved this kind of issue. One more architectural difference. So we talked about the operation, which is the layer normalization along with residual. So in the original transformer paper, which is attention is all you need, they have described this operation. They have positioned this operation after each sublayer. But in the GPT family, we have it before each sublayer. So before we feed it to a before we feed the input to multi-headed attention block, we do this operation. So we call it pre-norm or pre-layer norm. There, in the original paper, we have post-layer norm. What this means is before every sublayer we were going to do this operation of you know normalizing and adding the residual, whereas in the original paper we did it post each sublayer. What is a sublayer here? Mostly the sublayers that we talk about is the attention sublayer and the feed forward neural network sublayer. Okay, so I think we have mostly understood all the subcomponents of a transformer architecture that is used behind the GPT model. In the previous videos in deep learning talks, we've already talked about in detail about multi-threaded attention and token embeddings. So here we kind of took a bigger picture where we talk about all the subcomponents that are there in decoder-only transformers. And obviously, the idea of masking is not relevant in encoder portion, so it's only there in the decoder stack. So you don't have to confuse it with the architecture of BERT. And the idea of masking that we discussed only happens during the attention. So it's the causal masking happens at the attention sublayer. And yeah, I think pre-layer normalization and post-layer normalization is also one difference that is worth noting. And the idea of predicting the next token, where we use simple cross entropy loss as our objective function, as our loss function, that helps us to do next token prediction. And yeah, so all these subcomponents are more or less very much relevant even in today's transformers. We'll discuss how we have evolved from the early GPT models to the modern GPT models in the future videos. Thank you. I hope this was helpful. I hope you learned something new today. Thank you.